Alright, we are going to prove some things about the inner product as a function. Um, and so the things that we're proving here, these proofs aren't necessarily too difficult. They're more just the results themselves are sort of interesting, but also the other thing is that the notation is a little tricky. And I'll get into that with part A. Um, so if A and B are column vectors, so if we're given column vectors A and B, so these are going to be in Rn, let C be the column vector given by A, B. So you take A and B and stack them on top of each other. So then so now we're going to define the inner product as a function not from Rn cross Rn to R, but from R to N to R by the inner product of C is A, B. Okay, so what we're doing is we're taking the inner product of the first n entries in C with the last n entries in C. And so this is technically a different function than the one stated, but we need to work with this function in order to have a well-defined matrix IP prime. Because remember, IP prime is a matrix which represents a linear map. And so, let's see here. We know that if we're given a function from Rm to Rn, then, or if you're given a linear map from Rm to Rn, then the matrix of this transformation is an n by m matrix. No, it's an m by n. No, it's n by m. Yeah, that's right, because you plug in a vector in Rm, and so you're multiplying on the right by a column vector with m entries. So you need to have m columns in your matrix, and so your matrix is going to have n rows and m columns. Okay, so, but the main thing here is that if IP is a function from Rn cross Rn to R, well then what does the matrix of the... If you have a linear transformation from Rn cross Rn to R, what does the matrix of this linear transformation look like? It needs to have one row and how many columns? Well, you have to take Rn cross Rn, and there's no, way to put that into a number of columns. So you need to take Rn cross Rn and stack these two things on top of each other in order to define a matrix. So I don't like this problem in that they didn't specify that at the outset, and so it makes it a little confusing, but if you use this notation, it's going to be fine. And so this IP of C that I've written here, I'll refer to this as the same thing as IP of A comma B, just to make the notation match with the problem itself, but it's technically incorrect. Typically you call it abusive notation, and that's where the notation is technically wrong, but once you look at the notation, you understand what is actually literal, what is implied. It's not like a literal, you don't interpret the notation literally. Okay, so IP of C is going to be this inner product. So if we're writing this in terms of, so this is the sum from I equals 1 to n of ai bi. So if we're writing this in terms of the entries of the column vector C, then the entries of A are the first n entries of C, so we put Ci, and then the entries of B are the final n entries, so we take Ci plus n. Okay, and now this is something that we can work with, and we can sort of do the derivative techniques that we've learned from the past, because now we can see, okay, well, this is just the sum from I equals 1 to n. This is the projection onto the ith coordinate times the projection onto the I plus n coordinate. So, if we take IP prime and evaluate it at C, then this is going to be the sum from I equals 1 to n of pi I plus n prime, because the derivative commutes with summation, meaning like the derivative of a finite sum is equal to the sum of the derivatives. And so then from here you use the product rule, which I don't think I can fit on that line, so it's going to be sum from I equals 1 to n pi I prime pi I plus n plus pi I plus n prime. So this is going to be the sum from I equals 1 to n. I'm going to write ei to refer to the standard basis vector. So ei is a 2n. It's a vector in R2n, which all of its entries are 0 except for the ith coordinate, in which it has the entry of 1. So it's ei times ci plus n plus, and this is of course because pi I is really pi I evaluated at c. So pi I prime evaluated at c, well, it's just pi I prime is just a constant vector, and so evaluating it at c gives you that vector ei. And then pi I plus n evaluated at c is just whatever entry you have in the I plus n coordinate. So this is plus ei plus n times ci. And so if we write this as a vector, it looks like cn plus 1, and then you go up to c2n, and then you have entries c1 through cn. Alright, so if we write this in terms of a and b, we have ip prime of a and b. Again, this is abusive notation. Well, cn plus 1 to 2n, that's going to become b1 through bn. And then we have a1 through an. And then this is equal to, okay, so if a and b are column vectors, then these things that we've written here are row vectors. So this is going to be b transpose, the transpose of the vector b, followed by a transpose. So this is a 1 by 2n matrix. And so then the derivative of IP at A, B. So the derivative of IP at A, B, this is itself a linear function. So you need to plug in we need to plug in two vectors x and y, and these are going to be column vectors in Rn. And so what we do is we take this matrix B transpose, A transpose, and then we multiply by the vector xy. And so first of all, this is defined because B transpose comma A transpose, that's a 1 by 2n matrix. And then this xy that we've written, we've got two vectors in Rn, which are on top of each other, so they combine to form one vector in R2n. And so this is a R2n by 1 matrix. And so matrix multiplication is defined, and you end up with a 1 by 1 matrix, which makes sense because if you evaluate this the derivative at a point must be a linear operator from Rn cross Rn to R. So if you evaluate this linear operator at a point in Rn cross Rn, you should end up with a value in R, and that's exactly what you get here. So what this would look like is this would look like the sum of, let's see, you take bi times xi, and then you add the sum of all the ai plus yi's. And that would be what this looks like. Okay, and so from here, a similar argument gives us part B. And again, we do have to be a little careful about the notation and everything, but let's just go through that. So we've got h of a is defined as the inner product of fa and ga. So f and g are functions from R to Rn. So you can think of this as f of a is a vector in Rn, and you can think of the ith entry of this vector as f sub I of a. So when you take this inner product, you get the sum from I equals 1 to n of fia times gia. So h prime of a is just, you take this sum and you take its derivative, fia gia prime, and so we use the product rule here. Sum from I equals 1 to n, fi prime a gi of a plus fi of a gi prime of a. And this equals so the first sum is going to be f prime a transpose g of a. So I guess I'm being a little inconsistent in my notation of these inner products, but honestly I don't think it really matters. You just got to put a vector, when you're taking an inner product, you need to put vectors into both of the entries. I don't really care if they're row vectors or column vectors. Apparently Spivak does. But if he cares about whether they're row or column vectors in B, then he should have been more careful about defining IP in part A. But anyway, so it's a little inconsistent with what level of rigor and what level of abusive notation we're allowing for in these exercises. But yeah, so we've got the most important thing, which I don't even think is all that important. The most important thing is that the dimensions match up. Right? Yes. So if you're taking an inner product, you should plug the same type of thing into each entries of the inner product. So if g of a is a vector in Rn, so that's a column vector. Oh wait, isn't f prime? No, I think in the textbook we interpret g of a to be a row vector. And so f prime of a is definitely a column vector because f goes from R to Rn, so the derivative needs to be an n by 1 matrix, which is a column vector. So in order for it to match up with the row vector of GA, then it needs to be transposed. So there you go. I honestly don't really care about it that much, but if you want to make the if you want to make sure that the transposes of these vectors are the same, I guess you have to put in these transposes where I've put them. But more importantly is not the transpose itself, but the result, where you take the derivative of the inner product and you get this sum. And so now this is actually useful in the next part. So we have a function f whose absolute value is equal to 1 for all t. We want to prove something about the inner product of f prime and f. Okay, so we know that 1 equals the absolute value of f of t. So now let's square that. And then this, we still have 1 on this side. But then on the other side we'll have the absolute value of f of t squared. And we know that this is the inner product of f and f of t with itself. And then what we do is we take the derivative of both sides of this equation. So on the left-hand side, we take the derivative of 1, we get 0. And we take the derivative of this, and we know how to take the derivative of this. We just use part B. So this is going to be f prime of A transpose T. This is T. F prime of T transpose f of T plus f of T f prime of T transpose. Okay, but then inner products are symmetric, so you can flip around the f and the f prime of T transpose. And so then we notice that we just have 2 times f of T. No, we have 2 times f prime of T transpose inner product with f of T. And then we can divide both sides of this equation by 2. And we'll end up with 0 equals the inner product of f prime of T transpose f of T. And that's what we wanted to prove. So we're done there. Then finally, we want a function, a differentiable function f, such that its absolute value is not differentiable. And what you should think is, okay, so what's a function that we can take the absolute value of? What's a continuous function that we can take the absolute value of and end up with a discontinuous function? Well, you should think that it says not differentiable. And now I'm looking at this, because my answer to this seems very easy, and it almost seems a little too easy. But, okay, so it says find a function which is not differentiable. I'm going to exhibit a function which is not differentiable at one point. However, there do exist functions which are not differentiable at any point, and maybe we would need one of those. But those are, you'd have to use like the Weierstrass function, I believe, and that's non-trivial. They would not expect that in this exercise. Okay, so there are continuous functions which are which are nowhere differentiable. But for this exercise, we can just let f of t equal t, because we know, or you might have talked about in calculus, that the absolute value function is not differentiable. And that makes sense because it makes a point at x equals 0, or here it would be t equals 0. Alright, so let's prove this. Let ft equal t. We need f to be differentiable. F prime of t equals 1. So it's differentiable. But let's take the limit as h decreases to 0 of, we take the absolute value function of f at h. Here, I'll write it like this. Absolute value function of f at h minus absolute value of f at 0 minus h all over h. So this is the limit as h decreases to 0 of, well, the absolute value of f at h is just the absolute value of h, which, since we're taking the limit from the right, h is always positive, so this is just going to be h. Absolute value of f at 0 is just the absolute value of 0, which is 0, so that's 0. And then we just have this minus h over h equals 0. And so this tells us that if we're only taking the limit from the right, the derivative of f at 0 is 1. Or rather, f prime at 0 is 1. And that makes sense if you look at the absolute value function. If you look for x greater than or equal to 0, the absolute value function looks like is precisely the function y equals x, which has slope 1. So it makes sense that f prime here equals 1. However, if we take the limit as h increases to 0 of absolute value of f at h minus absolute value of f at 0 plus h over h, then we get the limit as h increases to 0. Well, here we're going to have the absolute value of f at h. We're taking the absolute value of h, and h is a negative number. So we need to switch the sign, so it becomes minus h. And then minus the absolute value of f at 0, that's going to be 0 again. Then we have this plus h, and this is over h still. And so this is going to be 0 over h, and so it's just 0. So this tells us that the derivative of f, the derivative of the absolute value of f, if we approach from the left, is going to be, in that case, if we take absolute value of f prime, not the absolute value of f prime, but if we take the prime of absolute value of f at 0, approaching from the left, we're going to get negative 1, because we have a plus here. And so if the function absolute value of f were differentiable at 0, then these limits the fact that these limits both yield 0 would need to imply that we're getting the same derivative as we approach 0. But that's not the case, because in one case we need to use minus h, and in the other case we need to use positive h. And so therefore f is not differentiable, or therefore the absolute value of f is not differentiable at 0, and so that's an example of what the exercise was looking for. So I guess this is not really the most interesting example. This doesn't really shed any additional light or give any additional insight onto anything. But I think parts A, B, and C are a little more interesting in talking about, like, not only can we prove things about differentiability of functions involving, like, addition and product and things like that, but we can also do more complex operations like inner products. So anyways, that's how we do this exercise, and so we're done.